Alrighty, physics. Let's get into it for this week. So we're going to talk about electric fields and kind of the last touch-up things before we go into circuits next week. And the reason why we have to talk about electric fields is because um, electrostatic force, right? The what we talked about last week with Coulomb's law is a non-contact force, right? We call a contact force anything that um, two things have to be touching each other in order to experience a force, right? A push or a pull. But we've already seen non-contact forces before. Gravity is a non-contact force. You don't have to be touching an object to experience a gravitational pull from an object. And when we have these non-contact forces, well, we have to talk about how much force and what direction is the force experiencing in the space outwards from an object. And so when we talk about electric fields, we're talking about if you put a charge in space, the area around it and the forces that would experience, or the forces that a charge away from that object would experience. Now it gets a little bit trickier because when we talked about gravity, gravity is only an attractive force. Where the electrostatic force, the Coulomb's law, can be a push or a pull, right? Two charges of the same positive or negative repel each other, and if you have two opposite charges, they attract each other. And so that gets a little bit more tricky when we're talking about field lines. Let's go into here. Now we are not going to actually use this equation. Just know that electric field strength, the E field strength, capital E right here, is just the force on an object or the force on a charge per charge. So how much force is experiencing per unit charge on an object? And we'll talk about this a little bit. So remember, when we did gravitational field lines, all the lines had to be pointed inwards because gravitational force is always attractive. When we're drawing electric field lines, we always, and this is the biggest rule, draw the direction that a positive particle would move. We always draw in the direction that a positive particle would move. When we draw these, we make sure that the field lines never cross, that they're always connected to the charge perpendicular, and the more dense, now this is a little bit kind of something that won't be touched on too much, but the more dense the field lines are, the stronger they are. Now, the easiest way for me to kind of explain this is to just show you what it looks like firsthand. So let's take this negative charge right here. So if I want to draw the electric field lines around this negative charge, I want to draw them in the direction a positive particle would go, which means when I am drawing my electric field lines, I am going to be drawing them inwards because a positive particle would want to be going inwards towards this negative charge. Now they should all be perpendicular to the, now it's a little hard for me to draw with my mouse, they should all be perpendicular to it at this point right here, close to the charge, but this is what the field lines look around a negative charge. They're all pointing inwards because that's where a positive particle would go. None of my field lines cross. They all go to the charge perpendicularly. And if I were to draw more lines here, I would just say that the field strength is stronger around this charge. The more lines, the more the field strength, as a general rule. Which it's not rocket science here in terms of the stuff that we're doing in this. That's a nice easy one, and you can imagine that the positive one is just as easy, but the only thing that's different between these two is because it's a positive particle and we're drawing where a positive particle would go. Well, now the lines are going to be outwards because a positive particle would repel another positive particle. And cool. Not too shabby. Easy stuff. Let's get a little bit harder. What about a negative and a positive together in one image? So if we were to draw where a positive particle would go, a positive particle would go away from the positive and towards the negative. So let's draw that first line here. Bam. And then we can also say that if it's on an angle, like if we put a particle right here, it would repel away from the positive and end up at the negative. And so we're going to see some curved lines here, a little curved line here, little curved line here. And then, well, what happens if I have a particle like right about here, in this area right here? Well, it's going to be closer to the negative than it is to the positive, which means that the negative is going to have more of a force on it, and so it won't even really deal with the positive, and it'll kind of just go straight into the negative if it's not in between. And the same thing if it's not in between on this side, it'll just push it away. It'll look something like this. Because if I have a particle here, now eventually these will loop around, by the way. I'll go all the way around. But if you have a particle here, because the positive is closer to the particle than the negative, it won't really, the force repelling from the positive is going to be way more than the force attracting from the negative, and so it'll just repel outwards. So that's your positive and negative. But what about if we have two of the same charges? Now that's a little bit more interesting. And what we're going to experience here is if we have a particle right in the center, well, the particle right in the center, directly in between these two, won't move, because the force pulling it towards each will be completely equal. And so if we have an equal force left and right, well, then it will be completely canceled out and it'll be in equilibrium. But if we have anything other than directly in the center, what we're going to experience is actually asymptotes. And so we have a real life use of asymptotes, something that you might have experienced in some math classes that you maybe haven't talked about in quite a while, but we have some asymptotes in physics as well. And once again, on the outsides, we're going to experience, sorry, my drawings are pretty poor with my mouse. Something along the lines of here. And so that's the electric field lines between two negative particles. Now you can imagine what would change if I were to take these two negative particles and make them positive. Well, what's going to change is just the direction of the arrows. It'll be the exact same setup of field lines, but the arrows would be moving away instead of towards. Okay, so that is my electric field lines. Now, let's take a moment to think. So say we have a positive particle right here and a positive particle right here. Now, I already drew some field lines around here. So what if I took this particle and I pushed it into the other positive particle? Would that be easy to do? The answer is no. These two particles don't want to be next to each other. And so in order to take that one particle and to just like push it towards the other positive, it's going to take a lot of force to get that one positive close to the other positive. It does not want to be there. And if it's going to take a whole lot of force and we apply a force over a distance, maybe some things are already clicking in your mind, force over some distance, that means that we are doing work on the particle. That means that we are giving the particle energy and we are doing work to that particle, which makes sense because if I take these two positives and I put them really close to each other and I'm holding them there and it takes a whole lot of energy for me to hold it there, a whole lot of effort, and I release that one positive particle, well, what is it going to do? It's going to zip away. And so that zipping away is actually potential energy. And that is kind of the questions that we've talked about here, is that it wouldn't be easy to move a one positive particle next to another. And if I let it go, it would zip away. And so that positive particle, as it's next to another positive particle, has potential energy. And this is the basis of circuits. Because what's going to happen is we call that electric potential difference voltage. And so voltage is the amount of work that you do on the amount of charge. So voltage as little v is the work you do per unit charge, right? That's charge, Q. And if we have some work that can be done on a unit of charge, well, then we could take something and we could put a whole bunch of positives on one side, we could put a whole bunch of negatives on the other side, and when we connect them, the particles will want to go away from the other like particles, and it can move some charges around. And that is the basis of what we're going to be talking about in terms of volts. And so voltage is electrical potential difference. It is the amount that one particle, one positive or negative, wants to get away or towards another positive or negative, right? Which gives us our main point for this week, which is a battery. All a battery is it's a setup that provides electrical potential difference, where if you plug in one side to one side of a circuit and the other side to the other side of a circuit, the particles, the charges, will want to get away from one plate, specifically the negative, we'll talk about what conventional current is next week, but essentially we have a positive side, a negative side, and the electrons want to flow through the circuit because of this electrical potential difference. They want to flow from the negative to the positive. And I asked you in the daily discovery, what is the difference between these two? Notice the actual kind of crazy part is a AA battery, a C battery, a D battery. These are actually all 1.5 volts. No matter what, even though this battery is bigger, it's actually the same voltage. It pushes the electrons the same amount based off of its electrical potential difference. This battery just has more electrons to push. It has more charge to actually push around the circuit. And so while the C battery doesn't have more of a push than the AA battery, it just has more electrons to push. Now that's an analogy that we will kind of touch up in the next weeks. But obviously, well, one of these batteries doesn't fit into it, and it's a 9-volt battery. A 9-volt battery has 9 volts of electrical potential difference. It's not all that crazy to think that a 9-volt battery has 9 volts where the rest of them have 1.5 volts, which is why the 9-volt battery can be used to power things that require more electrical potential energy to flow through them. It's also the reason why 9 volts, and we'll talk about a little bit more, dies a lot faster than any of the other batteries. You'll find yourself replacing 9-volt batteries faster than you'll replace a AA or C or D battery for the most part. It depends on what you're kind of dealing with. Some things are extremely efficient and don't need to be changed out. And so that's kind of where we're stopping for this week. We're going to talk about a little bit more, but right before we get done with it, I just wanted to do a couple practice questions just so that we are set for our multiple choice assignment. So remember, the equation that we're going to be looking at is the V equals work over charge, where V is voltage measured in volts. Work is just our work measured in joules. And Q is our charge measured in coulombs. So if it takes 14 joules of work to move 2 coulombs of charge from point A to point B, what is the voltage? Well, the voltage is my 14 joules of work for 2 coulombs. So this is 7 volts. Bam, nice and easy. And next one is, what is the electrical potential difference? Which, mind you, the electrical potential difference we just learned is the same thing as saying voltage. When we use 2 joules of energy to move 0.2 coulombs of charge. So what is the voltage when we use 2 joules of energy to move 0.2 coulombs of charge? Well, 2 joules energy, 0.2 coulombs of charge, that gives us 10 volts. Bam. Not too shabby. Sorry, can't see it. Alrighty, so that is where we're stopping for this week. Next week, we're going to build some circuits. Next week, we're going to look at kind of how we can use voltage in our everyday lives and actually kind of put this electrical potential difference to work. Cool. See you guys then. Bye.